Hello, my name is Jessica Fintzen. I'm a professor of mathematics, pure mathematics at the University of Bonn, and I study representation theory and number theory. I'm studying representations of p-adic groups and the Langlands correspondence. So what are representations of p-adic groups? What are p-adic groups? P-adic groups are matrix groups where the entries of the matrix are not complex numbers but are p-adic numbers. So these are numbers that arise in number theory that are coming from considering integers modulo p squared, and doing all of that at the same time, essentially. And then I study representations of these groups. So I look at how can I represent these groups using actually matrices over complex numbers. Well, that's the representations of p-adic groups that I study, and it has been very mysterious how to construct these representations. And I'm studying the construction of the building blocks of these representations, as well as how do we get all representations from the building blocks. What is the category of all these nice representations? And I also study how they fit into the local Langlands correspondence, which is the idea that on the one hand we have the representation theory, the representations of p-adic groups, and on the other hand, we have more number-theoretic parameters called L parameters. And the question is, how are they related? So the rough idea is that we have representation theory on the one hand, so the study of symmetries using matrices. And on the other hand, we have number theory, so the study of prime numbers and equations and how to solve equations. And there is a deep relationship between the two. And I try to study that explicitly and also in a categorical framework. There are a bunch of different research projects I'm working on. One project that I'm finishing right now is that we try to relate arbitrary representations to easier to understand representations, also in the categorical sense. So more precisely, if you study representations of p-adic groups, there is a notion of a depth. So a representation can either have depth 0 or it can have a positive depth. And sometimes we like to think of the representations as fish swimming in an ocean. So they are the ones that are at the surface, depth 0, and then the ones deeper down have positive depths. And so what I'm currently working on is to show that everything that's deeper down actually is equivalent to something of depth 0. More precisely, the whole category of representation breaks up into blocks, and the blocks that don't have depth 0 but that have higher depths are equivalent to blocks of depth 0. And that then allows to reduce a lot of problems about these representations to the depth 0 representations. And these in turn are much nicer because they are related to representations of finite groups of Lie types. So we reduce in that way questions about representations of p-adic groups to questions about representations of finite groups. That's one of the projects I'm currently working on. I also try to construct more representations and to fit everything then into the Langlands correspondence. And I should say that's also joint work with collaborators, so it's not just myself who works on that. I'm particularly excited that some of my projects are with young colleagues. So the project that I just described is together with Kazuma Ohara and a few others, who is still a PhD student. And the project constructing more supercustom representations is with my current postdoc, David Schween. But recently I moved to Bonn. I'm a professor at the university, but this semester I'm actually on sabbatical, so I'm visiting the Max Planck Institute. Well, I mean, to be fair, I'm often at the Max Planck Institute because the university and Max Planck Institute are not far apart. The Max Planck Institute has a lot of international visitors that come and go, so it's a very exciting place here as well. And I think it's important that the two math institutes, the Math Institute of the University and the Max Planck Institute, that they collaborate. So there's a lot of exchange between the two places. And they are both together also part of the Hausdorff Center. So we are all mathematicians who work with each other. Yeah, so there are many different Langlands correspondences, different incarnations of the Langlands correspondence. So I'm working mostly on representations of p-adic groups, which belongs to the local part of the Langlands correspondence. So the Langlands correspondence, well, there are, as I said, different incarnations. One is the local Langlands correspondence, where we really look at matching representations of p-adic groups with, on the other side, roughly Galois representations for Galois groups of local fields. Local non-Archimedean fields is what I work with. What I really work with is to try to construct an explicit correspondence. And so if I want to construct an explicit correspondence, you really need to know how both sides look like. And so I study the representation theory side in particular so that we can write down an explicit correspondence. And without knowing how the objects look like, there's no way to actually write it down explicitly. So that's one way I'm working on this. The other way is that while I say I study representations of p-adic groups, so that's a local problem, this is very important to go to the global side as well. So the global Langlands correspondence would be that you study automorphic representations and then Galois representations of global fields. And these automorphic representations, they are made out of all the representations of p-adic groups at various places, and then also representations of real or complex Lie groups in certain settings. And so the idea is that in order to get the global Langlands correspondence, you need to actually understand each piece, or not necessarily need to understand, but by understanding these representations of p-adic groups, I'm able to deduce new results about these global objects. So, for example, I have a joint work with Sorgu-Shin where we deduce results about automorphic forms and therefore automorphic representations by proving new results about representations of p-adic groups. So you can't really break these things apart. They have really, there are influences from the local world on the global work and the other way around. So in some sense, even though I start out with the local world, there are applications to the global world as well. And then the third thing that is coming up now in current work in progress and joint work in progress is that we are also looking at the categorical local Langlands correspondence. So this has become much more fashionable recently than instead of just looking at representations and representation of p-adic groups on one side, Galois representation, also called L parameters on the other side. One tries to put everything into a categorical framework. So one looks at the derived category of these representations on one side and some nice sheaves on the other side, and then tries to have a categorical correspondence. So one upgrades everything, and that's another thing that I'm studying right now. It's a good question. It comes together, but I think for us it's more like the Langlands program, it's more understanding this mysterious relationship. So there's some mysterious relationship between number theory and representation theory. And one tries to really understand it and build this bridge. So it's solving problems, but more so building the bridge and understanding what is this mysterious thing that connects everything. There are some people who just try to go around and say, give me a problem and I want to solve it. So it's less that, it's more building this whole theory, this whole connection, and figuring out what are the underlying secrets. Maybe I should say, in the end, this is still used to solve problems. In particular, Fermat's theorem, I think, is the most famous example where these deep connections were used to actually solve an explicit problem that has been around for a long time. So it's always a mixture. Yes, definitely since I was in maybe middle school or so. But at some point I took part in Olympiads by coincidence, and I really enjoyed that. I really enjoyed meeting other people who were interested in math, and somehow it was then clear for me that I wanted to study math and become a mathematician. I still remember that in high school I was mocked by that idea because people said, oh, you can't know yet what you want to do, wait until you start studying and then most likely you might hate it and don't want to continue. But I said, no, I know for sure I want to do a PhD in math, and it actually worked out that way. So I started studying mathematics and physics in parallel, so I also have a bachelor's degree in physics. I somehow liked pure math more than the experimental parts. I really like the proofs, that you can actually prove things and that they are then, once something is proven, it's true, kind of this idea I found very exciting. And then I decided to study math, do a PhD in math, and that I ended up in representation theory is just coincidence. That's a good question. I think in general, just the feeling when you have solved a problem or discovered a connection or figured out something, that's just amazing, in particular after having spent many years wondering how does it work? How can I prove something? And if you then at some point just see the missing piece and everything fits together, and the previous mess suddenly becomes like something nicely ordered that makes a lot of sense, I think that's a really nice feeling. So I've actually been once to Sydney, and the one thing that I still remember is that we had this tour on a ferry, and I was, okay, this is a bit ridiculous, but we had a good amount of fun, and I was walking on deck of the ferry on hands. I remember Jordi was there as well, telling me that he was learning a handstand, so I don't know how far he got by now. So.